Okay, how's everybody today? Okay, so a couple of items. One is quiz 5 Monday. Well, the usual thing. Here, I will actually not be here on Monday. I have to give a talk at University of Iowa. I'll be only away for a day, so there'll be a graduate student with me will not be giving this race, but I will be here the day after the day after that. I'll be here also the Sunday before. There was are there any questions? Questions at all? Okay. A couple announcements I want to make. One is that, so I have put up, I think I mentioned this already, more practice problems, as if you didn't have enough. So there's another 3G, and solutions, and I've updated the, and I mentioned last time we have these equilibrium problems, rotational dynamics problems. Some of these are really tough. I wrote these problems because when I was teaching that class at NC State, similar to this one, we used to put really hard problems on those tests, and students were complaining there were not enough hard problems, and so I made these practice problems. Your quiz is not going to be that tough, okay? So you don't get too stressed out about it. But there are some nice multiple, like I mentioned last time, there are multiple step problems where you have to put two concepts together, or maybe even three concepts together, and so you can use these problems to see whether or not you have those concepts under control. Okay. And I mentioned here, I also updated this list of practice problems according to quiz number. Here you can see. So I've updated for quiz 5 what the practice problems are. I even say 6 is too difficult, don't do that one. And then a few of these are actually quite difficult as well. All right? Now, related to this number, just remind myself, what was that number 6? 3B. Forgot which one that was. Let's just take a peek at that. Ah, okay. That's what I thought it was. Oops. So zoom in on this. This is the problem that I said was too hard. And this is related to, I think, the question you were just asking me. So there was a question about problems like this, because this is on your homework. It's a little too hard for the quiz, but it's fine for your homework. So, no, I don't write homework problems. It's just the way they are. So you have a string wrapped around a solid cylinder, and you want to know what is the angular acceleration of the cylinder as this mass is attached to the other end. Okay? So there's a bunch of things involved. You have to know a torque relationship between torque and moment of inertia and angular acceleration. Does everybody know that one? Okay. So that is the equivalent of F equals ma. That equals ma. Remember the analyze the second law? F net is equal to mass times acceleration. Change the F. What is the analog of F for rotation? Torque. Torque net is equal to what's the analog of mass in rotation? Moment inertia. What's the analog of acceleration in rotation? Angular acceleration. So it's torque net torque is equal to moment of inertia times angular acceleration. Everybody got that now? It's not that. It's nothing really new. You just convert the force to torque. You convert the n, the mass, to moment of inertia. You convert the acceleration to angular acceleration. So the torque net is equal to moment inertia I times alpha. So that's one of the things you need here. Okay. So. Yeah, rather than doing this whole problem out, which will be kind of tedious, let me give you the concept and a shortcut to how to do the problem. Okay, so you can do on the homework. As I said, I feel this is a bit too hard to give you on the quiz, but to help you on the homework, here are the concepts you need. So it's a little too far, a little too close. Okay, so for the basic part, there's the simple part of the problem was there's like two parts to this problem. You have a cylinder, so it's a solid cylinder. So remember, for a solid disk, uniform disk, the moment of inertia, this is given on your equation sheet, which I just remember that was another thing I wanted to talk about on the, you have the equation sheet here. Sorry, I'm going out of order here. I've forgotten that I wanted to do that also. Let's look at, oops, I don't want that. The equation sheet, the formula sheet. Let's just take a look at what it looks like. So this is the formula sheet. This is how Professor Iwazaki writes it. So it looks a little different from maybe how I would write it, but you should get used to what's on it. Okay, so you have the stuff. Sorry, I can't. Let's see. That's a little bit bigger. Okay, so you have the usual stuff with the conversion factors, and then you have the stuff we had before, but then you see some new stuff here. The cross product, right, it's written like this. This is the magnitude. The cross product A cross B is A times B times the sine of phi, and it's perpendicular to both. That's saying the direction of A cross B is perpendicular to both. That's his notation for writing vectors like this, okay. But then he has in terms of components, and this is the component formula for the cross product. I gave you that, if you were here last time, I gave you that very simple cookbook way of calculating the components of the cross product. If you want to just write down the formula, write down the answer from this formula, it's on your equation sheet, okay? So this is the x component of the cross product, this is the y component of the cross product, and this is the z component of the cross product. And then you have your integral formulas again, you have the stuff you had before. This is all the same as quiz 4. This is also the stuff in quiz 4. And then you have this new stuff. Okay, the circular orbit near Earth is kind of useless. We don't need it. This is also useless. But then you have the rotational dynamics. Torque is equal to R cross F. Okay, and then you have how to calculate the center of mass, moment of inertia. This is the formula here. We're not going to, well, okay, so maybe simple integral you could do. This is the parallel axis theorem. If you know the moment of inertia about the center, then you know the moment of inertia about some parallel axis that's shifted away by a distance d if the mass of the object is m. And then you have, this is what we're just talking about, torque net. Net torque is equal to I times alpha. You can rewrite it in terms of alpha. Okay, and then this is angular momentum here for a particle, angular momentum around for a rigid body. This is the rotational kinetic energy. And these are the formulas. This is actually why I wanted to pull this up. This is for various cases. If you have a hoop, a hollow hoop, this C is 1, meaning that the moment of inertia is m times r squared with no factor, where C is equal to 1. If it's a cylinder, if it's a solid cylinder or a disk, then it's 1/2. That's what this is telling you, 1/2 times mr squared. Is it clear how to use this? Right? You just put this coefficient on the front, it's 1/2. If it's a solid sphere, a uniform sphere, this is 2/5 mr squared. If it's a hollow sphere, it's 2/3 mr squared. Now, this is for a rod, meaning it's like a stick, a thin rod. Okay, something that's thin with a length L, and then if it's moment inertia about one of the ends of the rod of the stick, then it'll be 1/3 ml squared. If it's about the center, it'll be 1/12 ml squared. Okay, that's all on the equation sheet. Any questions about that? Okay, let's go back to what I was talking about before I interrupted myself on this. Okay, so for a solid disk from the equation sheet, you can get as 1/2 mr squared. Okay, now you can say, what happens if I have a string wrapped around like this? Let's first do the very simple case where I have maybe a tension T pulling on the string. Okay, that's the easier problem. Okay, so everybody's with me so far? Okay, so in fact, let me call it not T, let me call it F, because I'm going to write torques and you might get confused between T for tension and tau for torque, so I don't want that to happen. So let's just call this tension F. All right, now this is the center of the cylinder. Let's call the radius R. Okay, so if I want to know the torque that this force exerts on the cylinder, can anybody tell me what the torque will be? What times what? Yeah, everybody see it, right? So what is the formula for torque? Is the lever arm vector cross the force, where I have, here's the rotation axis, rotation. Okay, so here, and then let's say the force is acting over here. Then I have to draw this lever arm vector, or position vector, maybe just call it that. And then I have to take the cross product of R and F. Okay, does everybody remember that? That's torque. That was maybe a little while ago that we did that. And so if you want to get the angle between the two, that's fine. You can use that to get the cross product. But anyways, in this case, what is the angle between R and F? 90 degrees. Okay, so this is my R. So there's going to be a 90-degree angle here. And so when I get the torque due to this force, it'll be R times F, the magnitude of R times magnitude of F, times the sine of the angle between them, but the sine of the angle is, sine of 90 is 1. Okay? Everybody's with me so far? So what's nice about little pulleys or cylinders like this is the force will be perpendicular to the radial vector coming from the center. There'll be a nice 90-degree angle. Okay, so it's just going to be, okay, so I call it a small r, but let's just call it capital R because that's what I labeled the radius as. So it'll be capital R times F. Okay, but we also have another formula. Okay, so we have this other formula, I alpha, the net torque is equal to I times alpha. We just talked about that, Newton's second law. Okay. All right, so we have two formulas for the torque, so that means these guys are equal to each other. And I'm going to write down now an equation for the angular acceleration. The angular acceleration will be the torque, which is R times F, divided by the moment of inertia. Does everybody follow me on that? This part is not hard, right? You can do this. This up to this stage, if I were to ask you what is the angular acceleration of the cylinder due to this force, I expect all of you to be able to do that. That's supposed to be an easy quiz question. So this to this point should not be a hard thing. Okay. It would be R times F, that will give you the torque, and then you say a torque is equal to I times alpha. You solve for alpha, you get R times F divided by I. Okay, now what we're going to do, let's put more details here. The moment of inertia is 1/2 mr squared, so I'll put that on the bottom here. Okay. The next steps are what's a little complicated, and I'm just going to simplify this a little bit. Alpha, I'll cancel one of the r's. I have F divided by, I'll put the 2, with the 1/2 in the denominator becomes a 1/2 in the denominator becomes a 2 in the numerator, and then I have mr. Okay? Is everybody okay with that? Is that good? All right. Now the next thing I want to know is, that's the angular acceleration, but I want to actually know how fast, let's say I'm paying attention to some point on the string, let's say this point on the string. I want to know the actual linear acceleration of a point on the string. Okay? Everybody understand what I'm talking about? If I just, at this point on the rim, I want to know how fast it's accelerating. So what's the relationship between the linear acceleration and the angular acceleration? And notice I'm talking about here the actual, let's take a point maybe off through the circle here, okay? Oh, sorry. That's why nobody's saying anything, sorry. Okay. So this is like the, I have a wheel, okay? And I have a point here. I want to know the tangential acceleration of a point on the rim, how does that relate to the angular acceleration? What do I multiply the angular acceleration by? A is equal to AAT is equal to R alpha. So it would just be R alpha. Okay? Everybody with me on this? Okay. So now, what I can do, I have this formula for alpha. And so I can put this together. I have R times 2F over MR. Okay, that's nice. The R's cancel, so I have 2F and right. So now what I'm going to do is I'm going to do something kind of weird. Okay. I'm going to write this formula. I'm going to say F is equal to, I'll multiply both sides by M, A's. So I'm going to get rid of the, okay, let me do this in 2 steps, so otherwise you'll have trouble following me. I have A is equal to 2F over M. Then I have M times A is equal to 2F. And then I will write it as F is equal to M over 2 times A. Right? You're probably wondering why I wrote it that way. The reason I wrote it that way is that it's going to look like this cylinder is going to rotate and accelerate the way a particle with mass m over 2 would accelerate if you pulled on it with force F. Okay? Do you understand that? F is equal to ma, but notice that it's not m times a, it's m over 2 times a. So it behaves like a particle with mass m over 2. Does that make sense to everybody? Okay. I did all this gymnastics to get to this point. And now what you can do is you can basically think of this more difficult problem. So now if you have this, and you do have this on your homework, so I'm trying to help you with your homework. If you have this difficult problem, that if you have a cylinder with mass m, and you have another mass small m down here, okay, connected by a string, and you want to know how fast the acceleration is of this combined system, it's going to be just like, you remember we talked about these snake directions with these Atwood type pulley problems? Okay, it's exactly equivalent to this problem here, where you have an m over 2 mass wrapped around a pulley, and then you have a small m mass here, okay? It's exactly this problem now. Do you understand where I'm getting at? So all this complicated stuff with the rotation, the acceleration will behave like it was a particle, the mass was just a linear motion with mass m over 2. So if you can replace the cylinder by a mass where the mass is m over 2, now you just solve this problem. So then you do this curved direction s, this plus s direction. Remember how this goes? Does this work? Okay, yeah, this is how to solve that hideous problem. You can look on the hints how they help you solve this problem, but this is the fastest way I know how to explain this problem. I know you're probably thinking, if that's simple, then I wonder what the other explanation looks like. It's a rather difficult problem. Okay, so remember how we did this problem? There's a force mg that goes down, then we have a total mass of m plus m over 2, and then you say we have the force, you just divide by the total mass, and then you can get the acceleration that way. Yeah? Oh, okay, yeah. Maybe I should explain that. That's a good question. So here's, okay, suppose this is flat in both ends. Here's a cylinder, okay? So from the point of view of rotations, if I slice this cylinder into like a coin-shaped object, it would be a disk, but it rotates just the same way. It has no difference. In other words, this dimension doesn't change any of its properties. Okay? Yeah. Exactly. So the 1/2 came from the fact that the moment of inertia was 1/2 mr squared. If this was a hollow thing, then we would have ended up with capital N here. Right. Okay, if you got confused by this, this is not to help you with the quiz. This is to help you with the hardest problem on your homework set. Okay, that's the whole purpose of this. If you have questions, just email me. I'll try to help you out. Okay, let's get back to what we wanted to do. Let's start off with the quicker question. Let's do. It's possible, my memory fails me, it's possible we've done this problem before, but it's a good warm-up problem, so let's do it again in case we haven't. Okay, so it's 80 kilogram man and 60 kilogram woman are 7 meters apart on frictionless ice. They hold a massless rope and start pulling on each end. The question is, when they meet, how far has the woman moved? Okay, A is 0.0 meters, B is 3.0, C is 4.0 meters, D is 5.0 meters, E is 6.0 meters. Okay, and I'll give you that. By the way, when you take your quiz 5, if you read a problem and you don't understand what the heck it's saying, please ask questions about it, especially for those of you who are not native English speakers. If there's some word that you don't quite understand, like, I don't know, instead of saying uniform, they say evenly distributed, and you're not quite sure what that means, or somewhere like that. Please ask. That's not supposed to be something, you're not supposed to, well, we're supposed to help you if you don't understand. They're apart by 7 meters. Yeah, that's another thing. If you can't visualize what the problem is saying, badger the person. I feel bad now because I'm not actually going to be here on Monday, but you can ask the people who are supervising the place to help you. Yeah. Oh. Yeah, it was very easy. The first problem is easy. But when you pass the mass to the other end, then they accelerate into something more complicated. Okay, yeah. So this is so some of you are having difficulty visualizing. There's no picture up here. So try to so rather than just telling you what the physical thing is, well, let's read it together and try to see where it says 7 7 meters apart. That's all each man or 7 meters apart. Now they hold a massive rope. Okay, so you put a string between the two, and they start pulling on each end. If you start pulling on each end, the man goes towards the woman goes towards the man. The question is, when they meet, how far has the woman moved? So read each sentence over and over again until you get what each sentence is trying to tell you. If you're still confused and you don't know what to do here, this is the center of mass problem. It's all about the center of mass. The center of mass. Okay, so to give you a further hint, if you have a system of particles, the motion of the center, this is the principle of the center of mass motion. Okay? If I have a system of particles, I find the center of mass. The behavior of that center of mass is as if all the particles, all the mass of the particles are located at the center of mass. Okay? In particular, if there's no force, external force acting on the system, the center of mass will not accelerate. The center of mass is not moving to begin with, it will just remain where the center of mass is. So the problem, the key to this problem, is you find the center of mass remains at the same place. How far is the woman? Okay, well, I'll give you another minute, then we have to move on to other problems. Okay, if you haven't made a choice yet, go ahead, click in, just guess if you don't, so you get credit for the attendance part of it. Okay. All right, let's see what people said. All right, so a lot of people say C. Let's take a look at this. So have we done this problem before? Yes, we have. Okay, good. That's what I thought. The reason I can't remember is I've done it in some class, and it feels like it was this class. Okay, so I'm going to draw the x-axis here. I don't need a y-axis at all, so I won't even label it. So let's put the woman at the origin. The reason I put her at the origin is then I can calculate very easily how much she's moved, because that will be the displacement from the origin. And so now the man is 80 kilograms here, and so the distance apart is 7 meters. Okay, so let's find the center of mass of the system. The center of mass is the mass of the woman times her location, which is 0, plus the center, the mass of the man times his location, which is 7, divided by the sum of the masses, 60 plus 80, and then that ends up being 4 meters. Okay, 560 divided by 40 is 4 meters. So that's where the center of mass is, right there. The point is that the center of mass does not move because there's no external forces. The only forces are internal to the system. They're pulling each other inwards. So they're going to meet basically at the center of mass because the rope will have 0 distance. Okay, so that's why the woman moves. She moves. Woman moves. Yeah, 4 meters. Yeah, question. Yeah, absolutely. So you could have a situation like you could imagine. Well, this would be a more complicated problem, obviously, but now you push one of the participants. And now then what we'd do is you'd say, okay, I can treat the whole system like it's a particle, right? Then the total mass of the system will be the mass of the woman plus the mass of the man, all right? And then the physics would be then that the net force on the system would be the mass, the total mass, times the acceleration of the center of mass. This F equals ma. Okay? It's not really that complicated. Okay, yeah. You mean if you do it differently? In the drawing? Yeah, if I do it differently in the drawing, then what would happen, 80, 60, then what would happen is my center of mass would be over here, where it would be XCM is equal to 3 meters. Okay? But then you'd say, but the woman then moves 4 meters to the left. Yeah, that's all that would happen. All right, any other questions? All right, let's go on. I don't think I can do too many quick questions this time, so it takes too much time. So let's do some problems together so we can try to cover some ground here. All right, this is a problem that we put on at NC State a few times. Another center of mass problem that the students absolutely hated. I actually never really understood why this was so disliked. But anyways. Okay, so this was maybe it's because it looked like it was a simple problem, but it ended up being complicated. Maybe it's just deceptive. A 3-layer cake is constructed as shown. Each layer can be considered a uniform cylinder of height h. Okay? The masses from the bottom to the top are 3m, 2m, and m as shown. The distance from the bottom of the cake to its center of mass is what? So in other words, where is the center of mass of this whole system? Right? So in order to get the center mass of the whole system, what you need to do is you need to treat each layer and figure out what is its mass and where is its center of mass. Okay? So it's a multi-step problem. Maybe that's different. So let's first take this bottom layer. It has a mass of 3m. Okay? We're going to say, where is the center of mass of the 3m layer? The bottom layer, sorry. Okay? Because it's uniform, the height of the center of mass will simply be, is it clear to everybody? It would just be half the height of the layer. It's uniform, it's going to be in the middle of the center of mass, okay? Is everybody with me on that? So now what you do is you simplify. You say, all that cake gets squished down into a little globule, really dense piece of cake now. But it doesn't taste very good. It's at the center of mass. And it's going to be all here. Okay? Then we're going to take this 2m, or the middle layer, and we're going to ask, where is its center of mass? Well, it goes between, it starts here and it ends here, so just halfway in between is where its center mass is. Does that make sense to everybody? Okay? And so we're going to put all of its mass right here, and that height will be, this is h, but then another half h, so that height will be 3/2 h. You got that? Okay. Yeah, it's probably these steps that are a little confusing. And now then, where's the center mass of this guy? It'll be right in the middle here. So this will be 1/2 of h again. So you have 1h, 2h, and a half. 2.5, or 5/2 h. Everybody's good on that? So we've crushed each layer into little points. I have mass m here. I have mass 2m here. I have mass 3m here. Now I just need to get the center mass of these 3 points of cake. Okay? So the total mass will be m plus 2m plus 3m, so it's 6m. And then I do, okay, let's do the top layer. So I have a mass of m. Its height is 5/2 h. Okay, then I add the middle layer, its mass is 2m, times its height, which is 3/2 h. Okay. Everybody still with me on this? No? Anybody have a question? Okay. And then for the bottom layer, the mass is 3m. Its height is h over 2. And so I have 3m times h over 2. And then you add them together, divide by the total mass, 6m, and you get 7/6 h. Okay? Any questions about that? Everybody good? By the way, if you do have a question, please do ask me a question. It doesn't matter how long it takes. Just ask me a question. All right. Then let's go on. Let's do number 18. Okay. Here's a straightforward moment of inertia problem. We have two particles of masses. M1 is equal to 4 kilograms, and M2 is equal to 2 kilograms. By the way, this is practice problems 2G that I'm working from here. So, and connected by a vertical rod with two light rods here of length L1 equals 0.1 and L2 is equal to 0.2. Okay, L1 is 0.1, L2 is 0.2. The moment of inertia of this two-particle system about the vertical rod is what? All right, so one thing I should mention is if they say something is a thin rod or something, they mean that, and if they don't give you a mass, they mean that you're supposed to neglect the mass. Okay? However, if they do give you the mass of something, like a stick, if they give you a mass of a stick, and you don't put it in the problem, you're probably doing it wrong. Okay? We don't intentionally give you masses of things to get calculate moments of inertia or whatever, and then it doesn't matter. Okay? So if there's a mass in the problem, and you're trying to calculate moment of inertia or calculate torque or something, it's got to be, it pretty much has to be in your formulas. Okay? So don't neglect things if the masses are given. But in this case, the masses are not given, you're supposed to neglect them. So it's only the masses of these two masses that matter. So we have points essentially. Okay? We're neglecting the size of these things again. By the way, if you have questions about what you can neglect, like you might worry, what about the size of this thing? Well, the problem says it's a particle, so it doesn't really have any negligible size. Okay? All right. So the moment of inertia of a particle at a distance L from the rotation axis is ml squared. Everybody's good on that? Okay. So the distance from the particle to this axis is L1. So I have m1 times L1 squared, and we can just add up the moments of inertia together. Okay? It's not a vector, we just add them together. And so then we have this m2, the mass of this guy, times L2 squared. You plug in the values. M1 is 4. L1 is 0.1. M2 is 2. L2 is 0.2. And you add these together, and you get 0.12 kilogram times meter squared. Okay. Any questions about that? All right. I didn't have this on my list, but this problem is kind of tempting. Okay. All right. Here's a tough problem, but it's not what I would consider too hard for your quiz. So it's worth doing this. It's kind of equivalent to the problem I've meant to do, but since it's right here, let me do this one instead. Okay. This is an energy. Okay, so there's a bunch of concepts here. There's the concept of rolling. Okay, so when something is rolling, how fast it's going is related to its angular velocity. Right? So omega is the angular velocity, omega. Remember the W thing is omega. And if I do r times omega, that gives me how fast something is rolling. You guys remember that? Rolling? Okay. All right. The other concept is conservation of energy. All right, so a hoop is rolling without slipping along a horizontal surface with a speed of 4.5 meters per second when it starts up a ramp that makes an angle of 25 degrees with the horizontal. What is the speed of the hoop after it has rolled 3.0 meters up the ramp? Okay. All right, so when you read a problem like that, what you should immediately think about is, can I give you tips, good problem-solving strategy? Try to figure out what the heck am I being tested on? What concept am I trying to pull out of my memory banks or out of my equation sheet? Right? It goes up a ramp, clearly it's going to start to slow down. So I'm thinking, this sounds like what we did in quiz 4 with conservation of energy. Right? So if this was just a particle sliding up a ramp, a frictionless ramp, this would be a straightforward quiz 4 problem. Is everybody with me on that? So, but now we have it rolling also. So kinetic energy will involve the kinetic energy of rolling. So now you see, so it's testing me on two concepts already. So it's testing me on conservation of energy. It's testing me on whether I know the kinetic energy of rotation, the 1/2 I omega squared. Okay? Everybody with me on that? So now if I'm preparing for quiz 5, I have to ask my question, do I know how to apply conservation of energy? Do I know how to apply kinetic energy of rolling? Okay. And then there's a third concept that you have to have, and that's the connection between the rotational, the omega, how fast it's rotating, and how fast the center of the wheel or the center of the cylinder is moving. And that's the formula that gets written right here, that omega, or V is equal to omega times R, or omega is equal to V over R. All right, so there's three concepts in this problem. That's what makes this kind of difficult, but you need to know all of those three and put those together. All right, so now here's a picture of the diagram. By the way, because we're going to use conservation of energy, this angle, yeah, okay, so this is kind of a mean problem. All right, it does use the angle because it says 3 meters up the ramp. So first thing we're going to need to do is we're going to need to calculate how high up vertically it goes, because in order to use the conservation of energy, I need to know how high up it goes. Okay, so I have this angle 25 degrees. So this is 3 meters up the ramp. That's what you're given. So this is 3 meters times sine of 25, and that comes up to 1.27 meters. That's the final height of the how much the center of the cylinder of the hoop. Sorry, center of the hoop goes up 1.27. Okay, so for rolling without slipping, we will have kinetic energy of what's called translation. That's the motion, how when something moves, when it translates, when it goes from one point to another. The kinetic energy is just the usual formula, 1/2 mv squared. Okay. But then, because it's also rotating, we have a 1/2 I omega squared. Right? Now, they're connected because we are rolling without slipping. We have omega is equal to V over R. Any questions so far? Everybody with me up to this point? Questions? Usually when you're looking at this and you're being very quiet, you're thinking and you're confused about something. So is somebody asking a question? Yeah? Everybody's good? Yeah. That's why the radius drops out of the problem. Yeah. So now what we're going to do, in order to be able to deal with this problem, we're going to replace the omega by V over R. So we're going to put it in here. We have 1/2 I V squared over R squared. Okay. So everybody's with me on that? Okay, now the next step. Okay, I realize it's kind of a tough problem. But now we say that the hoop has a moment of inertia of mr squared. And so I can take this formula here. I put in mr squared over here. And I'll just get 1/2 mv squared plus 1/2 mv squared. That's what will happen. If I add those two together, the halves become 1. And so I get mv squared. Any questions about that? Okay, so these steps here, maybe this whole problem is a little hard, but these steps you're expected to know how to do. If I have something rolling without slipping, if it's, let's say, a hoop, then the kinetic energy will not just be 1/2 mv squared, it'll be 1/2 mv squared plus 1/2 I omega squared. When I plug in omega is equal to V over R, this and take I is equal to mr squared, I end up getting another 1/2 mv squared over here. And it becomes a full mv squared. Any questions so far? Okay, now I can feel your stress levels going up. You think, oh no, quiz 5 is going to be kind of tough. Yeah. Do you want me to write that out? Yeah. Okay, sure. I don't have space here, but let me write it out over here. Okay, so I have 1/2 K total kinetic energy 1/2 mv squared plus 1/2 I omega squared. Right? Oh, too high? Okay, sorry. Okay, now I have I is equal to mr squared because it's a hoop. Okay, so it's a hoop. And then I have omega is equal to V over R. Okay. So then I just copy this, mv squared, and then I have 1/2, and then I have mr squared, and then I have V over R squared. Okay. Okay, now this R squared will cancel out this R squared. So I'm left with 1/2 mv squared. Okay? And so then it becomes mv squared. So that's for a hoop. If this was a cylinder or a disk, then this would have been 1/2 mr squared. Okay? And then there would have been another factor 1/2 here, and it would have ended up being 3/4 mv squared. Okay? Is everybody good on this? Yeah, I expect you to know how to do this. This is sort of a key thing about rolling. What is the kinetic energy of rolling with a given speed, given a moment of inertia? Okay. So I just said, so let's say we have a disk. So if we have a disk, then I is equal to 1/2 mr squared. And so in that case, we would say K total is equal to 1/2 mv squared. Okay, it's the same formula, I omega squared, but now we have this being 1/2 mr squared, and this omega becoming V over R. Okay, and then when you plug this in, I will have the R squared will cancel the R squared in the denominator, same story, but then I'll have 1/2 times 1/2, I will get 1/4 mv squared, and so it ends up being 3/4 mv squared. Okay, questions about that? Yeah. Oh, sorry? Which part? This one? This one. Okay, it's the same as this one up here. The I is equal to 1/2 mr squared. Okay. And then I have the omega here is V over R, so it gets squared. Okay. So I will get 1/2 from here. I get a 1/2 mr squared. And then I will get V over R squared. And then I get the R's cancel. Okay. All right. Okay, so now to complete this, then you just use conservation of mechanical energy. You have K initial plus U initial. So you have the initial kinetic energy, m times V initial squared, so 4.5 squared, plus 0. You start from 0 height. And then for the final case, you have the final kinetic energy is m times V final squared, because that's the formula for the kinetic energy. The total kinetic energy times plus mg times the final height, 1.27. And so you have mv final squared plus 12.4 m. Then you set the initial energy equal to the final energy. You solve for V final, you get 2.8 meters per second. Okay? All right, we'll do a review of topics next time, and then I'll try to figure out a way to do some more problems.
Question. So, for this problem here, I understand how you did the center of mass. Yeah. But why is that just the sheet values?
Because they both meet there.
So the center of mass when they're there, or
Okay. They keep going when they hit each other. When they hit each other, there's a length of the room. They're on top of each other.
so they're at the center.
They're at the center.
So even at the beginning and the end, the center of mass does not move. That's right. So, okay, so then 1, 3. Okay. It's number 13.
Yeah, it's probably so. Yeah.
So for that one, these are just the heights, like they're like the Y kind of?
Yeah, just the Y positions.
Okay.